Thank you for the folks that organized this, especially Rhonda, who may have slipped out. But I know several people put a lot of effort into this, so thank you. And INC has been a home for me for a number of years now. And long before I came here, it was one of those things that was on the radar early in graduate school, seeing the impressive breadth of literature that came out of this institute. And so I feel like I've been at home for a while now. And I'm going to talk to you a little bit about some of the research we're doing to try to bring technology to medicine. TP touched on this a little bit, and again, as with Scott, with great breadth and depth. I'm going to just give you a few highlights of a specific, fairly narrowly defined approach that we're taking to, in particular, neurology, and how do we apply computer vision advances that are used deeply and broadly in many other domains to the field of neurology. A little bit of background. So as many of you may know, pharma has largely dropped a lot of their research efforts into neurologic and psychiatric disorders, which is a tragedy for society at large because of the huge impact the brain disorders have on individuals, their families, and society, a huge burden, right? And there's a number of potential reasons for that. I don't pretend to be an expert in the mechanisms as to why the private sector has dropped a lot of that research. But I think one of them has been the cost-benefit analysis, right? If it takes $1 billion to bring a drug to market, you want to feel really strongly that there's a good chance you're going to be able to recoup those costs in terms of future revenues, right? And despite the massive advances in molecular and genetics, biology at that level, there's many drugs that have been developed that have had very good scientific basis in preclinical trials and animal studies and have failed when they've gone to clinical trials and been tested in humans. But one of the elements of that whole cost-benefit analysis, the cost side, is what's the cost of running those clinical trials? And I would contend that part of the cost and the reason for the failure for some of those, at least a contributing factor, is how we rate the outcomes. Do the patients get better, right, with the treatment? And despite the massive advances in computational technologies and big data, machine learning, deep learning, yada, yada, and the massive advances in molecular biology, somewhat ironically, it seems that we're a little bit behind on studying basic things like behavior and phenotyping the patients, right? What do they look like? How do we quantify their symptoms and capture them? And that's not an easy thing. And it's part of the impetus behind the MOBI initiatives that the Swartz Center has undertaken to look at more naturalistic behavior. So what do I mean by phenotyping and why is this important? I'm talking about measuring symptoms, and the idea is both for diagnosis or screening, but also measuring severity. So are their symptoms less severe after a treatment, for example? And this is a simple concept, but incredibly important for people to study the epidemiology of diseases. You know, what's their prevalence and incidence? What's their relationship to potential risk factors? And also a lot of folks like ourselves that do pathophysiology research, whether it's with brain imaging, with functional MRI, EEG, people that do genetics, even postmortem pathology studies. And then also if you try to measure how things change with the progression of the disorders and their natural history, and this is particularly important with neurodegenerative disorders like Alzheimer's and Parkinson's. So again, I come back to the importance of clinical trials and how we measure the outcomes after treatments. And this is relevant in movement disorders, particularly for not just oral medications, but also deep brain stimulation, and for a lot of the folks that I'll be talking about today that get botulinum toxin injections or Botox to control their symptoms. And believe it or not, the state of the art for much of medicine, as you know, probably seen in your own experiences at the doctor's office, is observational. Right? You know, when it comes to diagnosing things or screening things, a lot of doctors will tell you, well, I know it when I see it. There's a handful of, either history clues or observational clues. And then when it comes to rating things, there's a whole broad swath of what they call clinical rating scales that normally are assessing patients on these simple ordinal scales of 0, 1, 2, 3, or 4, just like the pain scales of 0 to 10. It's just a subjective assessment of how severe you are. The fact that this is subjective, no matter how expert the doctor might be at observing these conditions, leads to a whole cascade of problems related to these problems of variability and therefore lack of reliability. For the same doctor seeing the same patient or a video of the same patient twice at different times, kind of the intra-rater reliability, and then also inter-rater reliabilities. So if clinical trials need to recruit 1,000 patients of a certain population, it's normally done at many different centers. And they're assessed by different doctors. And so if there's different doctors at different centers that are assessing them, then you have to factor in what's the variability from one doctor to the next, even if you have the same patient video that you're looking at, right? I'm going to focus on a particular, within the realm of neurology and the scope of movement disorders. The third most common movement disorder is called dystonia, and it involves a lot of abnormal involuntary movements. And on the left side here is depicted a rough taxonomy. There's generalized forms that involve many different parts of the body, trunk, lower limbs, etc. But by far the most common ones are called focal, and they involve only a certain focal region of the body. And most of those involve, does the mouse doesn't show up, either the voice box, the larynx, it's also called spasmodic dysphonia, or the hand. There's a lot of, well, there's roughly 1% of professional classical musicians suffer from a movement disorder called musician's dystonia, where they lose precise voluntary control over the fingers, especially when they're playing the instrument. But the overwhelming majority of patients have cervical dystonia, which affects the muscles of the neck, and therefore they've got abnormal head postures or tremor, or a form of dystonia called Blepharospasm, or Bleph for short, which involves abnormal blinking or squinching of the eyes. So you can imagine these things often get misinterpreted. Patients that have Blepharospasm, when they're at the grocery store or at the restaurant, people ask them, what's wrong, or are you upset about something? And it's just involuntary movement that they have no control over. There's no emotional valence to it. Let's see if this plays. So here's an example of a patient with Blepharospasm. So you see she's got kind of a tonic squinching of the eyes, and I don't know if it's evident in the video, but she has excessive blinking. And then what we've been working on for a number of years now, and a little piece of INC history here, the folks that I think Gert alluded to that developed CERT and therefore went on to commercialize it in the form of Emotion and then were bought by Apple, had developed a form of software to automatically capture facial actions from still images, and you can get them from a stack of images from a video. And they were using it largely to assess emotion from face videos. But when I first saw it, actually in one of our TDLC forums, I thought, oh, we've got to try this with Blepharospasm patients. And so we went on to evaluate this software, and I'll skip some of the technical details for the sake of time. But this was published a couple years ago now in Neurology, where we used it simply to quantify the proportion of time that the eyes are closed in patients during the standard clinical exam. And this is from a handful of patients, about 50 patients from a handful of different sites. And one simple test was if you have someone go through and tediously on a frame-by-frame basis mark each frame, are the eyes open or closed? Is it capturing that? And that's essentially what's being depicted here. And then this automatic eye closure measure, basically if you compared it with a lot of these different clinical rating scales, it exhibited convergent validity. It correlated with them, which is kind of your first proof of concept that maybe we could use this as an automated tool to measure severity in these patients. Now, there's not the question of precision so much as there's the point of consistency, right? If we take the same patient video and give it to two different computers or the software running on two different servers, the software is deterministic. It's not stochastic. It's not random. So you'll get the same response every time that you wouldn't get from doctors, right? And the other form of focal dystonia I want to touch on briefly, cervical dystonia. Here's an example. So you'll see this man's doing one of the typical neurologic exams that people undergo where you're asked to tap your fingers like this. But also he has some abnormal posture and a slight bit of head tremor, right? And we can capture this, both the previous CERT that the folks here developed and other subsequent open source software that we've been evaluating produce not only assessments of facial action units, but also head pose, or head posture estimates in 3 axes of rotation. So you can get an estimate of, and these are kind of like airplane terms, right? Pitch, roll, and yaw in terms of degrees or radians on a frame-by-frame basis. And then we can compose simple metrics from that during a standard clinical video to try to quantify what's the severity of their posture, how does it differ from one part of the exam to the next, do they have a tremor, what's the frequency of the tremor, what's the amplitude, and do these things exhibit some agreement with what the doctors say. And these terms map to some of the clinical terms that they're typically used. So here's the same video, and it's just showing, just to give you a sense of the dynamics of these things over time. It's more or less what you'd expect. One quick question, this goes back to the idea of using these things ultimately in clinical trials. This is a depiction of dynamics of pitch, roll, and yaw over a roughly, 6-7 second period of time. And this is before botulinum neurotoxin. So before this patient was treated, they've got a fairly severe dynamic, kind of a tremor. And then the same y-axis range after treatment, you see their symptoms are mitigated. Most patients don't have this good of an outcome, but this is just a visual illustration of how we could easily detect the treatment outcome here. One of the reasons I'm interested in dystonia is other movement disorders also exhibit this, but it's most prominent, it's almost diagnostic in dystonia, is that a lot of patients have what I call a task specificity, and the most common example is what the doctors call a sensory trick. So this applies to blepharospasm too, but some of the cervical patients, if they just, it's not a forceful push of the head, if they just lightly touch their chin, it'll help normalize their head position back to center. It's unfortunate that sometimes our language misguides our thinking, and this is especially prevalent in English, right? But the use of the term sensory trick can be misleading. Sensory stuff may be part of it, but of course there's also motor components here too when you're moving your hand to your face. And so really it's these tight sensory motor loops that are probably at play. But the fact that this can temporarily alleviate their symptoms suggests that we really need to look at the context and the task and the kind of present sensory state and motor plan and factor that into what their symptoms look like on a moment-to-moment basis, right? The doctors usually have a heuristic. If you look at this 20-step protocol and you ask them, well, when do you assess this or that? They'll just say, well, we look at it, we assess it at its worst. But it's funny because a lot of blepharospasm patients, they'll have severe blepharospasm when they're not talking. But if they're talking to someone, it'll be greatly relieved. These kinds of things and the phenomenon of musicians' dystonia only appearing when people are on the instrument is what led a lot of folks to refer these patients to psychiatry early on, thinking that this was all in their head. Well, of course it's in their head, it's in their brain, but it's depending on current sensory and motor state. So we also wanted to just do a quick sanity check, and this is just an illustration of it, of demonstrating that if a patient applies their sensory trick, and if you look at the abnormalities in their head pose and how that changes over time as they do the trick. In this case, this patient, like some of them do, puts his hand on the back of his head and normalizes his position. It's important for the basic pathophysiology research to be able to capture this. Because if we want to study this with EEG or in some other sort of mobile imaging systems, then that moment-to-moment dynamics is important. And it's funny because when you go out in the real world and you play with real data, it's always a lot more complex than the stuff you look at with simulations. I came from an engineering computer science background where a lot of people spend a lot of their domain in synthetic simulated worlds, right? But there's a number of challenging cases out there, and you can imagine folks with excessive facial hair. Actually, this guy on the left is able to correctly capture his face, but we've got one patient that has such a profuse beard and mustache that you cannot, even as a human, see where his lips are. And those are actually key for the landmark detections that the open source software uses to find the face, and everything downstream from it depends on that. So we've got one patient, for example, where we just can't do it with the current technology. There might be other ways to get at it, but that's just an interesting example. And then this woman here with her hand on the side of her face, the software does fairly well with this. It's robust to this, which is important for our patients that use these sensory tricks and have their hands up by their head. Because among the landmarks that they use are things like jawline. So we are working with a large consortium of people that are interested in dystonia research. It's called the Dystonia Coalition. And they have thousands of patient videos collected from about 20-odd sites around the world, mostly in North America. So what we're trying to do is build up the machinery to try to do this in a systematic fashion and look at how our metrics can capture symptom severity across a broad swath of patients and really get at some statistical rigor as to how well this stuff holds up. So in the case of tremor, let me just explain the axes here. On the x-axis is the clinical rating of the severity of their tremor, and on the y-axis is just a log scale representation of the power and their dominant frequency of the oscillating tremulous movement of the head. There's a lot of details, devil in the details behind this, but it's just meant to give you a rough sense that at a crude level we can capture the severity of their symptoms. And this is just kind of a first pass look at things from one step of the protocol where they're nominally holding their head still. So I want to keep this brief and just mention a couple of future directions. And I touched on this tremor stuff. Part of the reason this is important, there's different forms of head tremor. And in dystonia, in cervical dystonia, that's one of them. It's called a dystonic tremor. But people with one of the most common movement disorders called essential tremor also can suffer from head tremor. And I've been to numerous conferences or meetings that involve primarily neurologists, and it's intriguing to watch many expensive people spending a lot of time debating, is this, looking at videos, is this dystonia, or is this dystonic tremor, or is this essential tremor? And you'd think that we would have been beyond that by the year 2019, a long time ago, but these are still areas of debate. What is step one in medicine, right? And so, they go around in circles talking about heuristics to try to capture that and distinguish one from the other. But one idea is, let's be agnostic to it, look at some objective quantitative metrics of what the tremor looks like, and see, do these patients cluster into a bimodal distribution in two groups, or is it really a continuum? Or what does it look like objectively? So that's one thing we want to look at, is the distinction between dystonic and essential tremor. And then we also want to get a handle on sensitivity. So a lot of these folks don't get properly diagnosed for 5, 10 years even. And of course, that prolongs or postpones the whole cascade of treatment and management. And so if we can develop rapid, easy, objective screening tools at least that might lead someone to an earlier diagnosis, that could be really clinically important. And then naturally this stuff lends itself to telemedicine. It's easy to envision the whole pipeline of doing this stuff on phones and through web servers with all the appropriate authentication, security places or protocols in place. So the simple take-home message is that these modern advances in computer vision, machine learning, while applied to many other domains, can do a lot for medicine, and especially providing objective measures in areas of neurology where you've got a very observational science currently, and the symptoms are very visual or visible. And these are important not only for clinical trials, as I've alluded to from the beginning, but also into research into the underlying brain mechanisms. If we've got a very tight temporally detailed handle on what the symptoms look like, that constrains circuit models of what's going on internally, which is really what I'm more interested in long term. So thanks. There's many folks that are really behind these efforts, including a lot of clinical collaborators around the world, and a handful of organizations that have supported us, most recently the DoD's Congressionally Directed Medical Research Program. And happy to catch questions later. Thanks.